we're gonna finish the class. So I'm gonna just do a brief recap of what we did in the last time. And then today we're gonna conclude by showing how to derive an optimal sampling rule for the Bayesian case. So the last time we were concluding the best policy identification scenario. We derived a sample complexity lower bound for BPI, and it's very similar to the best arm identification one. The problem is it's hard to solve the optimization regarding computing the optimal expression strategy in this case. So what we did was find an upper bound on the characteristic time that holds for all W's. We can also check the lecture notes here, since it's a bit better than my notation. So in the lecture notes, the result that we derived is this one, which says that the characteristic time for each W, you can see the definition of the characteristic time for a given W here, it's always upper bounded by this U. This is a relaxation. And the idea is simply to try to enlarge the set of alternatives. And this idea can be applied also to other problems whenever you need to find an upper bound on the lower bound. And usually this idea can help you try to characterize the characteristic time. This is also an idea, I think, that we used in other papers. Another idea to upper bound the characteristic time is usually to use a suboptimal exploration strategy. So if you remember, for best arm identification, what we did was plug in a suboptimal W, and then we derived an upper bound on the characteristic time. Here, instead, what we did was to relax the set of alternatives to derive an upper bound that holds uniformly for every W. So for every W, it holds. And then the idea is exactly as in track and stop. What we want is try to track the optimal exploration strategy that we compute at each time step using an empirical estimate of the NDP. So we denote by U star the optimal relaxed characteristic time. We define also an empirical version. And what we do is simply plug in the current estimate of the NDP and solve the relaxed characteristic time with respect to W. The only issue of the analysis here is that W is a stationary distribution with respect to MT, the empirical estimate of the NDP at time t. And then what you want is that your average selection frequency, so the average visitation of state action pairs, you want this vector to try to track this stationary distribution, which is changing over time. And this is the main issue of the analysis. So if you remember, in track and stop, what we wanted was to ensure that this quantity converges to the optimal W star. Because if it's converging to the optimal W star, the optimal exploration strategy, then you can show that asymptotically you are exploring according to the W star, and so asymptotically you are reaching optimality. So this is the main issue of the analysis. I didn't do the proof the last time because it's quite involved. And basically it relies on using an ergodic theorem that tells you that the average visitation converges to the stationary distribution. So to guarantee this result, we need to ensure some properties first. And the properties that we need is, for example, that the expression strategy that you use at each time step assigns probability, non-zero probability to every action in all states, for example, so like a uniform distribution. And then we also need to know what is the stationary distribution we're converging to. And we know it's this one. And then, I mean, once we know these things, it's quite easy to prove these 5 properties. But first, we need to ensure that we are selecting all the actions with non-zero probability, and we also need to ensure that our estimate of the NDP converges to the true estimate. So, and if you remember from track and stop, if we don't have a good estimate of the NDP, then the allocation that we are computing at each time step, the W star, might be very different from the true W star. And so you're trying to track a solution that maybe it's very different, and this will lead you nowhere. So what we wanted is also to ensure that our estimate of the NDP converges to the true one. So we derived a result that says you compute WT star at each time step, so the optimal strategy for MDP MT at each time step. To ensure that we are converging to the W star, what you want is to add some an additional exploration strategy here. So from this WT star, we derive what is the oracle exploration strategy. So you compute WT star, and then you can define the oracle policy at time t. So this is like the exploration strategy for MDP MT. This is simply WT star SA divided by the probabilities of all the actions. And then to guarantee that we are selecting all actions with non-zero probability, we will do a convex combination between this expression, this oracle policy, and some other policy that we call a forcing policy. So this forcing policy can be chosen in different way. The most simple way is just a uniform. And when you select it as a uniform, or later I also discuss another choice, you can show that in communicating MDPs, you are guaranteed that you will visit all state actions infinitely often. And this comes from the fact that in a communicating MDP, you can always find a way to go from one state to another. So if you can guarantee that an action will be sampled infinitely often in a state, then you can also show that you will visit all the states infinitely often. And based on this result, then you can also show the ergodic result I told you before, and finally show that this average visitation frequency converges to the optimal stationary distribution. And this was basically it. I didn't go too much into the details because there are a lot of technicalities. And then we started the Bayesian pure exploration problem, only for the fixed budget. So just as a reminder, this is the problem we are trying to solve. We are trying to find an inference rule, a sampling rule, that maximizes the probability that at the final time step, we can correctly guess the true hypothesis. So here it's for a fixed model theta. So we parameterize the model by theta. And this is the objective in the frequencies case. So in the frequencies case, we have this d hat. It's the inference rule. It's a mapping from data to hypothesis. We have d star theta, which is the true hypothesis for a model parameterized by theta. We also define an history as this sequence of observations and actions. So the history at time n, and capital N is the total budget, is the first observation, the first action that you took, then the second observation, so on, up to the final observation. And remember that the sampling rule is a collection of policies. Each one is a probability kernel over the actions, and you are conditioning on the entire history that you have seen up to that time step. So the policy at time t, it's a probability kernel condition on capital HT.
Sorry, I missed last factor, but why the last element is xn instead of an?
So the question is why the last element is xn. So in this model, we are modeling the interaction a bit differently. So we assume that you have an initial observation, and then based on this observation, you select an action. In the bandit case, this initial observation is simply null. It doesn't, you don't observe anything. But like in MDPs, in Markov decision processes, usually the initial observation is the initial state.
Yeah.
So this is a more general way to model the problem. So if you think of it, you observe an initial state in an MDP, you take an action, then you observe the next state. So in a trajectory, the final element will always be an observation of the system. So when we pass to the, well, first, before moving on to the Bayesian case, just as a reminder, we call p theta the transition function of the next observation given the past data and the last action. And when we pass to the Bayesian case, what we need to do is, first we need to define a set of parameters. And we also assume that we know how the parameters affect these distributions of observations. So let's call the set of parameters capital theta or big theta. And from here, you can also define what is the set of models, capital M. And this set of models is simply a set of these tuples as you vary theta. So this tuple is the observation space, the action space, the transition function, and the true hypothesis for that theta. And for a fixed theta, we can define what is the distribution, the probability measure over trajectories. And the idea is that we just need to define the probability measures over cylinders. So the cylinder that we consider here is A, not to be confused with the action space. It's basically the Cartesian product of these sets. So C1 belongs to the sigma algebra of the set of observation, and B instead belongs to the sigma algebra of the action space. And then because of the UNESCO-Tulcea theorem, you can show that the probability measure can be defined this way. And we only need to consider sets of this kind to define uniquely the probability measure, just because when you do the sigma algebra of product of spaces is equal to the product of the sigma algebras. So this is just a technicality, but in the end, what's really important for you is that the probability of a trajectory, it's basically the integral over the first observation, then the integral over the first action taken by the policy, condition on the first observation, and so on, until the last step. And once we define the likelihood, so the probability measure of a trajectory, we can also define the joint measure over trajectories and models. And assuming that we call Q the prior over theta, so over this set. So assuming we call it Q the prior over theta, we can define the joint measure in this way. So probability of that the trajectory belongs to some set A, theta belongs to some set M. It's simply the integral over M of the probability that HT belongs to A for a fixed theta. So this is like a conditional distribution integrated over the prior. And from here, we can also find the marginal over trajectories by simply choosing big theta here. So when you select big theta, this integral is not over M, but it becomes over theta, big theta. And this is simply the marginal over trajectories. And now the question is, when can we find the posterior distribution over models given a trajectory? So to well define a posterior distribution that we can use, we need first an assumption of domination. I mean, the posterior distribution is defined also without this assumption. But if we want to use, if we want to find something that is of practical use, we need this assumption in the end. Without this assumption, you can only state that the posterior distribution exists, but you cannot like write it down in a closed form. So what this assumption tells us is that the distribution of observations is dominated by some other measure lambda that does not depend on the trajectory and does not depend on the time step and on the model. So for example, the Gaussian distribution is dominated by, so the Gaussian measure is dominated by the Lebesgue measure, for example. And once we have this, we can define then the Radon-Nikodym derivative, which gives us a density f. And then we can define the likelihood of a trajectory in terms of this density. So once we have this likelihood, it's possible to show that basically the posterior over models given ht will be a ratio of integrals of likelihood ratio of likelihoods. And so I didn't write the expression, but you can find it in the lecture notes. Yeah, so once we have this, we have the posterior distribution over models. And once we have the posterior distribution over models, we can also define the posterior distribution over the true hypothesis, which is simply the push forward measure here. Yeah, and then we arrived here at the last result of the last lecture, where we show what is the optimal inference rule. So the lemma says that for any sampling rule pi, for any t, the optimal inference rule is the one that maximizes the posterior distribution. So for any given trajectory, capital HT, the inference rule, the optimal inference rule is simply the argmax over the hypothesis of the posterior distribution over the true hypothesis. And the proof is quite simple. So what we're gonna do today is show what is the optimal sampling rule, and then we are done with this topic. Yeah. So the last time, basically from our last lemma, what we showed is that this quantity here it's essentially equal to sup over pi of the expectation with respect to the sampling rule of this quantity here, where R capital N Hn is equal to max over the decisions of the posterior distribution at time n of the star theta being equal to d given Hn. So this comes from the fact that the optimal inference rule is the one that maximizes the posterior distribution. And it's not the I chose the notation R here because essentially this will become like a real word. So I did it on purpose to write these quantities in this way. And now what we need to show is try to understand what is the optimal policy here. And to do so, first we need to define what is the posterior transition function. This will become useful. So for a given trajectory, ht, action A, we define the posterior transition as p bar of the next observation. So xt plus 1 that belongs to some set x given ht so this posterior transition is simply the integral over the next observation of what? So it's simply gonna be the integral here of this xt plus 1 given x and a. Let me So it's simply gonna be the integral over the next observation of the transition function for a fixed theta, average over the posterior distribution of the models. So this is the posterior distribution over theta given a trajectory ht, and this is simply the transition function for a fixed theta. So what we are going to do now is try to define what is the optimal value of the problem. We are going to do it in a recursive way. So we're going to start from the final time step. So we're going to define the value of a policy pi in... so we're going to define the value at the last time step, not with respect to a policy, but simply for a fixed trajectory. So let's call h and the trajectory at the last time step. And we are going to define it to be simply the reward at the last time step. And then from now on, I define the Q function at time step t for a given trajectory ht and action A to be the expectation over the next observation But where do we sample this observation from? We sample it from this posterior distribution, this transition here that we defined before. So it's an expectation over the next observation sampled from the posterior transition of what? We're going to define it to be of Vt plus 1 computed in Ht plus 1, where Ht plus 1 is equal to Ht. Let me write it a bit smaller. Vt plus 1, Ht plus 1, where Ht plus 1 is equal to Ht A xt plus 1. So let's see if this is if this makes any sense. For example, in t equal capital N minus 1. What we have is this expectation over the next observation of what? Of R and Hn, where Hn is simply equal to Hn minus 1, A xt plus 1. So for n minus 1, it's fine. We now define Vt, a time t, to be equal to the maximum over actions of the Q function. So recall, we are doing all of this just to find what is the optimal policy, and we are doing it in a recursive way, in a backward way. So we start from the final time step, which does not require any action. We define what is the value at the last time step. Then we define, in a general way, what is the Q value at any time step. So at the step n minus 1, it's going to be equal to this quantity. So the expected value of Rn. And then we define, for any step, we define Vt to be equal to the maximum of the Q function. So now the question is, does this induce like an optimal policy, this reasoning? So if we define pi t star given a trajectory to be equal to the argmax over actions of q t h t a, is this an optimal policy? And what we are going to show is a very simple result. So lemma, we have that for any policy pi for any time step t, the expected value given this sampling policy of Vn, capital Hn, given that you are given some data time t, this is smaller than Vt computed at Ht. So for any policy pi, what we're going to show is that this holds. And then what we are going to also see is that this holds with equality if we are going to use this pi star here. So now let's maybe skip the proof of this for now. Why, if we have this, can we show that pi star is going to be optimal? So from before, remember that we have this expression that we are trying to optimize, right? So now let's say that you are given some data time t. Let's say it's the first time step. So you know the first observation, because of this lemma, we know that this is upper bounded by v1 of x1. Okay? Now, if we integrate with respect to x1, the first observation, the inequality still holds, right? But we also know that this inequality holds for all time steps, and it holds with equality if we use pi star. So this v1 here, so we also know that this v1 x1 So just replace here pi by pi star, and here use 1. So what we have is that this is also equal to this expectation. Now let me just rewrite it in one single expectation here for simplicity. And the result is basically shown, because if we now optimize on the left over all policies, we know that this quantity is always upper bounded by something that doesn't depend on any policy. But then because of the previous lemma, we know that this is exactly equal to this quantity, which depends on pi star. So pi star needs to be the optimal solution. So I hope this is clear. It's very simple. So this is the quantity we want to optimize. We know that this holds, this inequality holds from the previous lemma. This quantity doesn't depend on any policy. So for any policy, this is strictly upper bounded by this. But then we know that this holds with equality when we use pi star. So this quantity is equal to pi star, and so pi star achieves the optimal. So we're gonna now prove the lemma. And we are gonna use a backward recursion to prove it. So we do it for backward inclusion recursion. So it means that we start by selecting t equal to n, which holds trivially for the last time step. Then we assume that it holds for t plus 1. What we want to show is that it also holds for time step t. So we know that it holds at time step t plus 1. So what we're going to use is simply the tower rule to try to deal with this. So by the tower rule, you can integrate over the next observation to get ht plus 1. But now you know that this is upper bounded by vt plus 1, ht plus 1, given ht. But what is the definition of vt plus 1? So remember that q, t, ht, a is equal to and we also know that vt is defined as the maximum action of qt, ht, a. So this expectation is integrating over x prime, right? I hope you can see that. So this is also equal to expected value of Qt, Ht, pi t, Ht. And we know that when we use pi star, this is also going to be equal to Vt, Ht. So in general, this is an upper bound because Vt is defined as the maximum over action of Qt. So this Vt plus 1, we are simply, the difference between Ht plus 1 and Ht is that there is an action to be chosen and there is a next observation. But the action is chosen according to pi t. And we assume pi t to be deterministic for simplicity. So this is the action chosen by pi t at time t. And then here, this expectation, it's basically this expectation here. It doesn't really depend on pi anymore. So it's expectation over x prime. So this quantity here, basically. And then we know that Vt is the maximum over actions of Qt. So this quantity here, it's upper bounded by this quantity. But this is an equality if we use pi star, because pi star is defined as the argmax over A of Qt. So this is an equality. And the same, we can also show that this quantity will be an equality here. So yeah, that's pretty much it for this lemma. So we have shown that this quantity for a general deterministic policy is upper bounded by this one, which is what we wanted to show. And the two inequalities holds with equality if we use pi star. So maybe, I don't know if you have any question about this. Is it clear why it should hold with equality here? So the reason, maybe it was not super clear now that I think of it, but so in when we do the backward induction, so it holds at time t equal n. Then the assumption that we make at time step t plus 1 is that it holds. So when we use pi star, it holds with equality. Okay. So that's why in the end, we can also apply it here, that it holds with equality. Because we know that at time step t plus 1, this holds with equality when we use pi star. But for another policy pi, generic is simply an upper bound. And then this inequality simply comes from the definition of Vt. So yeah, that's it. If you don't have any question, we can take a break. And then what we're gonna do is simply go over some of the slides I presented last Friday about this entire line of research and look at some numerical results. So let's take 10 minutes break. Okay, I think we can start again. So during the break, there was one question regarding the fact that we are using the entire trajectory, the entire history, and maybe it's not sufficient. Maybe you can use some sort of belief. So the idea is that usually, depending on the environment, you're probably gonna have different beliefs. Also, it's not clear like how you define the belief over what space, and using the entire trajectory allows you to use all the information that that it's available to you. And the overall idea is just to, in the end, use modern neural networks to let the neural networks understand from data directly what is the optimal lower dimensional representation of the data. So this is just a formalization of what's going on, but in the end, the transformer will try to learn something that is lower dimensional. So in this last part of the lecture, we're gonna go through some slides. We're gonna recap the main ideas of what we did. So the problem we are facing is essentially a problem that Chernoff came up with in the 50s. So the problem of designing experiments to try to understand some underlying phenomenon of a system. So you start by designing a first experiment, you get some evidence from the system. Based on this evidence, you rule out some hypotheses that are not true, and then you design another experiment, you get new evidence, and so on, until you're sure of what is the true hypothesis. And sure enough, he was PhD student of Walt, the famous guy of the bullets of the airplanes in World War II. If you're familiar with this image, probably you know it. Let me put full screen mode. So pure exploration is only what a statistician would call active sequential hypothesis testing. So it's the machine learning term that we use for this setting. So here, I'm just comparing between exploration and exploitation. So in bandit problems, in reinforcement learning problems, there is the issue that you're observing a reward, and usually what you want to do is you want to minimize regret. But to minimize regret, you need to select the good actions, but you don't know the model. So how can you choose the good action if you don't know which action is good? So you need to perform a bit of exploration to understand which action is the optimal one. But in our case, it's different. When we apply pure exploration to bandit or RL problems, you don't care about bad actions. You can select any action. The important thing is that you maximize the evidence. But already this idea of maximizes the evidence should ring you a bell that probably the problem of maximizing the evidence can be cast as an RL problem. So that connects also to the last thing that we discussed today. And for what problem is this useful? Well, we can use it for performing tests to detect cancers, to improve recommendation in recommender systems, quickly identify faulty sensors, or more in general for any active search problems. And now there is a very simple example that I like a lot, is this one where you have to guess what is the image about, and you are allowed only to select a few pixels at a time. And you want to stop as soon as possible. So you start by sampling some pixels, then another region, and so on. And what you want to do is to identify what is the image about. So after some time, you probably are able to guess that the digit here is 9, and you should stop once you are confident about the label of the image. So this is like an application of the Bayesian setting that we saw today. But let's go back to the best arm identification, because this is where everything started. So in best arm identification, we'll not go over again the details. We are trying to understand which arm is the optimal one. We are trying to find this A star nu, where nu is the distribution of the rewards. And we are trying to find this A star with some confidence level delta. Now, if you remember, we only did the tabular case, but there are also other cases. to consider. There is like the linear case where the rewards have a linear structure. There is the case with feedback graphs. So in the case with feedback graphs, whenever you select an arm, which corresponds to a vertex here, you will also observe the reward of the arms that are connected to this vertex. So this is the vertex of arm 2, this is the vertex of arm 3, and so on. When you select arm 1, you will also see the reward of arm 2, arm 3, 4, 5, and of arm 1. What makes it tricky is that maybe you don't know the graph. And also there are some activation probabilities of the edges. So for example, the probability that you will observe the reward of arm 2 when you select arm 1 will be G12. And you don't know this probability in general. Then there are also other settings with unimodal structure and so on. Here we have the definitions. I will not go over these definitions again. We have the sampling rule, we have the inference rule, we have the stopping rule and the best arm identification. And the problem we are trying to solve is this optimization, where we are trying to find an algorithm, which is a composition of the sampling rule, the recommender rule, and the stopping rule that satisfies this constraint. So it minimizes sample complexity subject to this constraint on the correctness. And for this problem, if you remember in the first lecture, we went over a very simple example to understand what is the intuition that we want to test the efficacy of two drugs that we model with Boolean responses. And let's say you have accumulated already some data, and from this data you can compute the empirical efficacy of the two drugs that we are going to call p hat n1, p hat n2. So now one of the questions I asked you was, okay, let's say you have this data. What are you going to do next? And if you remember, what I told you is to think in terms of what is the worst case scenario. The worst case scenario is when the two probabilities, the true probabilities, will be very similar. Because if the true probabilities are very different, it will be easy for you to understand that one drug is better than the other. But if the true drugs are similar, it will take you many more samples to understand that, right? So let's say then this is the right intuition, that P1, it's approximately equal to P2 or equal to P2. So what should we do in this case, given that we know that we have these two empirical values? If we think that in the worst case scenario, P1 will be equal to P2, it means that the true value must belong to some convex combination of these two empirical averages. In fact, after in the first or in the second lecture, when we derived the optimal solution for the optimization problem of the lower bound, we show that the alternative model has an average value that is equal to this convex combination of the empirical means. So in the first lecture, I just gave you the intuition, but then later, when we derived the sample complexity lower bound and we solved it, we show that this is actually indeed the case. And this is also the parameter of the alternative model, of the optimal alternative model. And then in that example, I told you then we should select the next drug to use according to the drug that maximizes the amount of information that we get from the system. So the one that maximizes this divergence between the empirical mean and this adversarial mean. So the idea is we want to maximize the evidence against the worst case scenario. So we need the first ingredient, how we quantify the evidence. We can do it through the expected log likelihood ratio. And then the worst case scenario is simply the alternative model that basically minimizes this log likelihood ratio. So it's an alternative model that could have generated the data. But since it's an alternative model, it needs to have like a different optimal arm. The reason why it needs to have a different optimal arm is because you want to rule out the false hypothesis. It doesn't make any sense to test against models with the same optimal arm in general. So for the purpose of deriving the lower bound, we need to compare with this set. And then we are simply going to take the worst case scenario from this set. And from here, from the log likelihood ratio, we also showed what is the data processing inequality, which tells you that this expected log likelihood ratio is always lower bounded by the Bernoulli-Kerr divergence of these two parameters. This is the probability under the true model of some event E, and this is the probability under the alternative model of the same event. And by choosing the delta probably correct event, this one, so the event that you have misidentified the correct arm, you can show that this quantity will be d delta 1 minus delta. It's lower bounded by d delta 1 minus delta. And so the expected log likelihood ratio is lower bounded by this d delta 1 minus delta. And as delta becomes small, this is roughly log 1 over delta. So we have this expression. Next, what we did was, okay, we have optimized with respect to the alternative model, but how do we find the optimal sampling rule? And the idea is to parameterize the number of samples. So we parameterize the number of samples. So we first normalize it by the sample complexity. We set this quantity equal to WA. This represents the sampling of arm A. So the proportion of times we should sample arm A. And once we introduce this parameterization, this is a distribution over arms, we can simply optimize over the distribution over the actions. So we take a supremum over W that belongs to the space of distributions over K items. And this is how we derive the sample complexity lower bound. We also show that the optimal sampling rule here, W star in the Gaussian case, is roughly proportional to 1 over the gap squared inverse. And when you select this specific sampling rule, we show that the characteristic time T star, so the result of this optimization problem, is upper bounded by this quantity. But we also show the lower bound on T star, which is basically the same quantity up to a constant factor 2. So in the Gaussian case, we are able to show what is basically the value of T star up to a multiplicative constant. Here it's a very simple example where we try to compute what is this W star, so the optimal expression strategy for the bandit case, this example. And what's interesting is that not necessarily the optimal expression strategy will assign more probability mass to the optimal arm. For example, in this case, the optimal arm is arm 2, but then the optimal expression strategy is assigning more probability mass to the second best arm. And this is usually the case in bandit problems with unstructured, so without structure. It's quite common to see that the optimal expression strategy will allocate more probability to the top two arms. But in problems with structures, this is not the case anymore, and you might have different patterns depending on the problem. Then from the lower bound, we also explained track and stop. So the idea is that the lower bound tells you what is the optimal sampling strategy, but we don't know the model. So what we do is we use an empirical estimate of the model, compute the optimal expression strategy for that empirical estimate. And then what we want is we want the average selection frequency to track this W star T, so the optimal strategy for the model that we have at time T. And we use this sampling rule. We didn't use this exact sampling rule. We used another one, but it's quite similar. So the idea of the sampling rule is that you want to ensure that all the arms are sampled sufficiently often. So for example, this sampling rule that we see here, whenever an arm has not been selected at least at the rate square root t, we are going to sample that arm. And otherwise, we are going to select the arm that most deviates from W star t, or the sum of the W star. So the idea is we need to track the W star t. Asymptotically, we know that it will converge to the true W if we keep sampling all the arms, and we can guarantee that the model is well estimated. The lower bound also tells us when to stop, because you should stop whenever you're close to T star log 1 over delta, but we don't know the model, so we need to pay an additional price that is usually logarithmic in T. And we also show that we can use Wills inequality with an appropriate super martingale to show that at the end, the stopping rule will be something like this. As the characteristic time, the empirical one, that multiplies a threshold rule that is log 1 over delta plus log t. And using this threshold rule, we show that we can guarantee correctness, but we can also show that we have asymptotic optimality. Now, the stopping rule that I showed you in the lectures has a suboptimality constant of 2, but you can show that there are better threshold rules that guarantee this optimality here. Some extensions, there is the feedback graph case. So in the feedback graph, as I told you before, each node represents an arm. Whenever you select an arm, you will observe the reward of that arm for this graph. So this is the bandit model. But for example, in this graph, whenever you select A, so the first arm, you are also going to see the reward of all the other nodes. But if you select any other nodes, you will not observe anything. And then you can have different graph structures. You can have this ring, or you can have the loopless clique, where everything is connected, but whenever you select an arm, you cannot observe the reward of that arm. So for this problem, we can show a similar lower bound as in this unstructured case. And what changes here is that the sampling policy will come into play here in the constraints. So the graph structure will affect what you're going to observe. And basically, we can define a quantity that is called the observation rate, which is simply the matrix vector product between the graph adjacency matrix and the sampling policy. And for Gaussian rewards, all of this simplifies to this simple expression. So here we see the effect of the observation rate that multiplies the gap squared inverse. And here we see that the observation rate is equal to the transpose of the adjacency matrix that multiplies your sampling distribution. But it's not all roses, because in the case where you don't know the graph activation probabilities and the rewards are Bernoulli, whenever you observe 0, you don't know if it's 0 because the reward was 0 or because maybe the edge did not activate. So in the case where the edge have probabilities and you don't notice probabilities, you can always come up with an alternative model that resembles the true model, and you can show that the characteristic time will diverge. So there are also some impossibility results in this case. So depending on the problem, we might have different solutions. And in general, it's also hard to solve this max-min problem. It's hard because maybe sometimes this set of alternatives is non-convex, but in general, even solving a max-min problem is computationally difficult. So it's not easy, and it depends on the problem that we need to solve every time. For example, in Markov decision processes, the alternative set is usually non-convex, which is what we have seen in the last few lectures. So for best policy identification, I will not go now over the notation. We have the MDP defined in this way. We have the state action spaces, the transition function P, the reward function R. For a Markov policy pi, we define the discounted value as the expected sum of the discounted rewards under policy pi. We define V star to be the optimal policy, so the maximum value we can obtain for any when we plug in the best optimal policy here. We can define the Q function, the action value function. And so we derive during the lectures also a lower bound for this case. And the problem is that this alternative set of models is in general non-convex. The reason why it's non-convex is because the value function, you can see it as a ratio of polynomials. So the value in each state is the ratio of two polynomials in the transition functions. So we have a non-convexity because of the transitions. And so it's very easy to come up with two alternative models, P prime, P second, where those are alternative models, but the convex combination is not an alternative model anymore. So we lose convexity. So what we did was try to derive an upper bound of the lower bound that is convex in W. We call this the relaxed characteristic rate. And we show that for each W, the characteristic time is upper bounded by this relaxed characteristic rate in W. And this relaxed characteristic rate depends on the suboptimality gaps, on the minimum gap, but also on the variance of the optimal value. In the lectures, we did not have the variance, just for simplicity. We had the infinity norm, but you can show that this result also holds in the L2 norm. And when you do that, you obtain the variance of the optimal value. And the algorithm design is essentially the same as track and stop. We have only the issue that we need to track stationary distribution. And this is a bit more involved. I briefly explained the ideas about that. But apart from this, the core ideas is essentially the same as track and stop. Then there are some extension of this problem. Like there is the multi-reward best policy identification, where essentially, let's say we are playing a game. I give you a set of rewards. And then I'm gonna say, okay, I want you to explore now. I want you to collect data so that when you stop for any reward in this set, I want you to be able to compute what is the optimal policy for that reward, only using the data you have collected so far. So this is a sort of adversarial game where you know what is the reward set, but you don't know what reward I will pick from this set. So you want to explore with respect to the worst reward in this set. So you collect data, and then when you stop, you want to guarantee that for any reward that I will choose, you are able to compute the optimal policy for that reward up to some confidence delta. So you want to guarantee that you are not able to estimate the optimal policy up to some probability delta. And this is different from the reward-free case. In reward-free, we are considering all possible rewards. But here, in some applications, we don't care about all possible rewards. In some applications, we only maybe care about a finite number of rewards, or maybe a small subset of rewards. So for example, in multi-objective RL, it's very common to consider different rewards. And now the question becomes, how do we explore when we have so many rewards? In other problems, you don't know what is the right reward function, and you want to test them out together. So this is another application where you have multiple rewards. Another extension is the multi-policy evaluation. So let's say you want to do policy evaluation. And the question is, what is the optimal way to collect data to do policy evaluation? So what is the optimal behavior policy to do policy evaluation of some target policy? So no one really did this analysis for the instance-dependent case. So what we did in this work was to not only provide the results for single policy evaluation, but also extend to multi-policy and possibly also for multiple rewards. So basically the question is, I give you a target policy, I give you also a set of rewards, and what I want you to do is, I want you to collect data, and when you stop, I will give you a reward from this set of rewards. And using the data that you have collected, I want you to be able to compute the value of that target policy for that reward up to epsilon accuracy. So the data you need to have collected needs to be of good quality, because otherwise you will not be able to give this guarantee that for any possible reward in this set, you have at most epsilon accuracy with at least confidence 1 minus delta. And then we also extended it to the case where maybe you also want to evaluate multiple target policies. So this condition is essentially telling you that the probability that you will misestimate the value of any of these target policy on any of these rewards is at most delta. And you can use the same techniques from the best policy identification to derive also this result. And you can show what is the sample complexity for this case, and you can also show what is the optimal way to collect data for this problem. So from here, then we moved on to the Bayesian active hypothesis testing problem. We only discussed the fixed budget, but here in the slides I will talk about the fixed confidence setting. So remember that we have some hypothesis space. Here in the slides I'm using capital H and not D, as we did in the lectures. We have the dynamics of the environment, and we have also the true hypothesis. Here I'm using H star, not D star. Also, I'm not using the parameter theta, but I'm using directly the model P of the dynamics of the environment. And we can construct a prior over a set of environments. So it's our belief of M. And the problem that we are going to try to solve in the fixed confidence is this problem. We are going to try to solve this infimum over all possible stopping rules, over all possible sampling rules and inference rules that minimize the sample complexity subject to this correctness constraint. And what we saw today, or the last time, was we showed that the optimal inference rule, it's basically the maximum of the posterior distribution of the true hypothesis. And secondly, what we showed today for the fixed budget is that we can define a reward that allows you to define a Q function. From this Q function, you can find the optimal policy. So we can use RL to train a policy. And what's important is that the reward is not something that we define, but it emerges naturally from the problem definition. So this proposition is about the optimal inference rule, which is the result that we saw the other time, that the optimal inference from data to hypothesis is the argmax over the hypothesis of the posterior distribution given this trajectory of data. And another simplification we can do here is that we can define a stopping action, and we can set the augmented action space to be the union between the old action space and the stopping action. And then we can define the stopping rule to be simply the first time step when the policy will select the stopping action. So this is the time at which we stop. And you can show that this doesn't change the value of the problem. This is admissible. And the next thing we do is to study the dual problem. So we're going to study a dual problem because when we study the dual problem, we can define the reward function. It's interesting to understand if there is some gap So if the duality gap is 0 here, is something that we still don't know. But when we look at the dual function, it comes very natural to define what is the reward. We can also guarantee the delta correctness for the dual problem under some assumptions. And this is the dual problem we are looking at. So we are defining this b lambda, where lambda is the Lagrangian variable. And here we have minus the sample complexity plus lambda that multiplies the term that we had in the constraint. And for this dual function, we can show that we can define this reward. And using this reward, we can also define this Q function. So this reward is simply -1 for every time step you took that you didn't stop, plus lambda that multiplies the value of the maximum of the posterior at the time step you stopped. Defining this reward allows us also to define this Q function, which is simply the reward plus the value of not stopping. And given this Q function, it's possible to show that the policy that maximizes this Q function is a solution of the dual problem. So we have the dual problem to solve. We define this reward. From the reward, we define the Q function. And then what we can show is that the policy that is greedy with respect to this Q value solves the dual problem. So this is the most important bit. What's interesting is that a solution of the dual of this problem is not necessarily, doesn't guarantee that we have the delta correctness. This holds for any lambda. So now the problem becomes, can we still guarantee correctness for any lambda? In general, no, but you can guarantee that at the maximizers of the Lagrangian variable under some assumption, the policy pi star computed in lambda star, so the optimal of the dual variable, this policy will guarantee the delta correctness criterion. But how do we update the lambda? So the lambda will be updated using basically a gradient descent approach. But we come back to this later. Now the question is, how can we use this result? So the result, we're going to use it in a very simple way. We will make the assumption that we have access to a prior over models, that we can sample trajectories from this prior, so that we can learn the sampling rule and the inference rule from this prior. And then once we have learned these two models, we can apply these two models on a real problem. And we're going to use transformers to handle the sequences of data. So the transformer will try to learn low-dimensional representation of the data and do all the heavy work for us. So there are indeed two phases here. There is a first training phase where we are training both models. So we are training the inference model to approximate the posterior distribution of the true hypothesis. And then we use this model that the inference is learning to compute the reward that we're going to use to train the exploration agent. So after training is finished, we are simply going to deploy the sampling rule and the inference rule at in some problem. The sampling rule will sample some data until it decides to stop. And then once you have stopped, you have a data set that you're going to feed to the inference rule, and the inference rule will output what is its guess of the optimal hypothesis. So indeed, we can see this method as some way to produce an exploration strategy that is able to collect data of good quality in the end. How are we gonna train the inference rule? So we can train it with the cross entropy loss. So we are making the assumption that we are sampling trajectories from a simulator, from a prior. And so we also know what is the true hypothesis. So we are gonna do a cross entropy loss where we use as target the true hypothesis. And this is in expectation equivalent to minimizing the Kerr divergence between I and the posterior distribution, the true one. And for training the policy, instead, we use the reward function that we defined before. But there is something here to note that the loss that we use, it's made of two terms. And the second term, basically, it's accounting for the fact that you can always evaluate the value of stopping at any partial trajectory that you have collected. So here we are simply maintaining a data set of trajectories. And in DQN, you sample from this data set a batch of partial trajectories. And for each partial trajectory, we can always evaluate what would have been the value of stopping at that point in time. So we can add this additional term to improve the efficiency of learning. And instead, this initial term accounts for the fact that maybe you didn't stop. And so you have the penalty of -1 for not having stopped at that time stop. Last but not least, we have the update of the Lagrangian variable. And as I said before, we are going to simply use a gradient descent update on lambda, where basically here you are taking the partial derivative of the dual with respect to lambda. We are assuming that I and pi are sufficiently stationary so that the gradient descent then will look like this quantity here. And hat p is an empirical estimate of this probability here. So this is the final algorithm in the end that we call ICP, in context pure exploration. We have the first training phase where we have access to this prior from which we sample data. We collect data, we put this data in some buffer, and then we use the data from this buffer to train the inference model and the policy using the cross entropy loss and the DQN loss I showed you before. Once we have trained these two models, we're just going to deploy these two models at inference time, use the policy to collect data, and then once the data is collected, make a guess of what is the optimal hypothesis using the inference model. So some numerical results. So we saw like already some examples with the binary, with the digits at the beginning. We're gonna look at that again. So the first example is, can ICP learn how to do binary search? So this is the case where you have a vector of elements. These elements are sorted from small to big or the opposite. And here, whenever you select an index, you're going to observe -1 or +1, depending if the index that you selected is smaller. So the value at that index is smaller or bigger than the value you're looking for. So the element you're looking for, we are going to call it H star. And we can see that for different sizes of this vector, the mean, the average number of samples needed by ICP is in general smaller than the maximum number of samples requested by binary search. And it's also able to guarantee the best accuracy possible. Then there was the example I showed you at the beginning, where you have to select pixels, and then you want to stop as soon as you understood what is the image about. But one question you might ask is it really adaptive? I mean, is it not enough just to sample the center? Is it really learning an adaptive strategy? So what we did was to compare with a uniform distribution of sampling, so sampling uniformly at random in the image, and we also compare with a contextual multi-arm bandit approach that uses deep neural networks. And what we did was to compare how the region selection changes across digits. So we use a pairwise chi-square test to compare how the sampling differs between two digits. And here you can see in the image, like for example, between 3 and 8, there is a chord here. This chord represents the p-value that the two sampling strategies are similar for digit 3 and digit 8. So in general, ICP seems to show different exploration strategies for different digits. For 3 and 8, it's very similar, but it makes sense because 3 and 8 are also very similar digits. But in general, like the uniform and the contextual multi-arm bandit, they are not adaptive. They are not adapting to the true underlying digit. So here, I think this is good evidence that ICP is learning an exploration strategy that adapts to what is the true underlying hypothesis. And here you can also see what is the average accuracy and the average number of regions used by ICP. And in the last examples, we have the magic arm bandit problem. So this is a bandit problem when one of the arms that we call the magic arm encodes information about the index of the best arm. So we are going to encode the index of the best arm through some invertible mapping phi. So we define the mean reward of the magic arm to be equal to this mapping evaluated at A star. And the reason why we choose an invertible mapping is because what we want is to see if the agent is able to learn how to invert this mapping, because if it's able to do so, then it's able also to recover what is A star. So ideally, in the best case scenario, you should be able to recover the index of the best arm in just one sample, if it knows how to invert the mapping. And we define the rewards to be Gaussians. The variance of the rewards will be equal to 1 minus sigma m squared, where sigma m is the variance of the standard deviation of the magic arm. So whenever the standard deviation of the magic arm is 0, then in that case, we require only one sample, because you can see exactly mu m, and if you know this mapping, then you can invert it. So during training, what happens is that ICP will learn what is this mapping on its own without that we have to tell what is this mapping. And then at inference time, it will use this knowledge to solve this problem. So here on the left, you can see the plot of the average stopping time versus the standard deviation of the magic arm. And when the standard deviation of the magic arm, we see that it takes exactly just one sample to solve the problem, as we expected. As you increase the standard deviation of the magic arm, it will start to require more and more samples. And after a certain point, it will not sample the magic arm anymore, because it's simply there is too much noise, and it just doesn't make sense for the agent to sample the magic arm. Remember that the standard deviation of all the other arms is 1 minus the standard deviation of the magic action. So as the standard deviation of the magic action increases, the standard deviation of all the other arms decreases, and the exploration agents will start to sample the other arms after a certain threshold. And you can see it here, the percentage of times the magic action was sampled versus the standard deviation of the magic action. As this standard deviation increases, at some point it will stop completely to sample the magic action. But overall, it seems to achieve very good sample complexity in general, and also the right level of correctness. So that's it. I hope you learned something from this class. I know it was quite technical, but I think overall it went good. And thank you for attending. Yeah, if you have any question, otherwise I'm just gonna briefly describe some open questions. So there are some open questions about non-asymptotic exploration. For example, in the MDP case, all the results are are asymptotic, all the results. Another question is also, is there a better way to characterize the exploration that we need to do for estimating the model. Like in track and stop, in navigate and stop, we require to estimate well the model to guarantee that asymptotically we have the right kind of convergence. But what is the optimal way to estimate a model? Usually we add some uniform exploration, but is this really the best we can do? Is there something better we can do instead of adding just some uniform noise to guarantee that all the actions will be sampled? So this is still not clear to me. What we discussed in this course is simply what is the optimal way to explore to account for the aleatoric noise of the problem. So the aleatoric noise of the problem is usually the noise of the rewards. But then there is the problem that there is also the exploration because of the parameters. We don't know the parameters of the problem. What is the optimal exploration that we need to do to estimate well the model? That's something that we still don't know. And it's also not clear how to like formulate this as an optimization problem. So in general, what you saw in this course are just how to characterize optimal exploration to deal with the fact that the problem is noisy, but we didn't touch the subject of what is the optimal way to estimate a model. I hope this question is clear, but it's a very pressing problem for me actually to define this problem and to find a solution to this. Another open question is like, can we design ICP for a frequentist case and not for the Bayesian case? Honestly, I don't even think it's probably a good question, but it's an interesting question, but it's probably not super useful. And the reason why it's not useful is because I came across a theorem that is called the complete class theorem. And basically what this theorem says is that in problems where the parameter space is compact, you can show that Bayes solutions are actually optimal in general. And this is an interesting result, actually. So for any method that is non-Bayesian, you can always find a Bayesian one that is at least as good. And this is very interesting, I think, because then this can motivate the reason why we should use Bayesian methods. Now the problem becomes, is the parameter space compact? And also another subtlety is that we need to have a good prior. So if you don't have a good prior, then you cannot guarantee this complete class theorem. But if you do have a good prior, then any method you can think of, there is always a Bayesian one that is at least as good. And maybe this is something that we should also discuss more in one of our group meetings later in the future. It's a result that I just found in a book from the 50s. Yeah, then other questions are unanswered, like for ICP in the fixed confidence, we are looking at the dual problems. Is the duality gap with respect to the primal problem 0? In which cases it's not 0. And that's very interesting to know because, first of all, we want to estimate how far we are from the optimal value of the true problem that we want to solve. The dual problem is not the real problem you want to solve. But if the duality gap is 0, then it's equivalent to the primal. Another reason why it's important to understand if the duality gap is 0 is because in case the duality gap is always 0, then in a sense we have shown that we can always convert this problem to an RL problem. Because on the dual problem, we can apply RL. It's not clear that we can apply RL on the primal problem. But if the duality gap is always 0, then the two problems are the same. And so we can always apply RL. So this is more of a theoretical question, obviously. But it's very interesting for me. So I would like to thank you again. And yeah, I hope you enjoyed that.